Let's get started to talk about linear regression. First of all, we are going to revisit the concept of supervised learning, and we are going to move on to the linear model. So earlier this semester, we discussed the multiple types of machine learning. So one of such type is a big chunk of methodology that is supervised learning. So informally, supervised learning is nothing but drawing a line. So regression, the problem that we are going to tackle today, where you have a bunch of data points and you want to draw a line that is summarizing your data the best. And on the other hand, classification, this is another type of key problem in supervised learning. So in supervised setting, you're going to classify or you're going to discriminate blue or red dots on the data space. So each of those colors represent different classes. And your goal is to find out a line that separates those two classes the best. So this is the informal idea of supervised learning, and where the formal definition could be where you have given data set and that consists of n sample. And each sample comes in pair. X is the input, Y is the output. And our goal is to learn a function that represents the relationship between input and output. So two types of problem, regression and classification, where we have discussed that where they are distinct by the type of the output. So when the output is a continuous value, we call that as a regression. When the output is a discrete value, we call that problem as a classification. And speaking of the notation, where we have defined all these already, so X is the input, Y is the output, and we are talking about the cases where output is a single dimension. So where we are looking at the output value is scalar, talking about the input, the vector is given for the input. Capital D is used to notate the data set, and small d is used to represent the input dimensionality. So given that regression is again Y value is continuous, and we want to predict the real value to target Y given the dimensional input vector X. So X is the input, and like we discussed last time, it has a multiple alias name, so independent variable, feature, or predictor, or covariate, and so on. And Y is the output value, and it also has the alias name like dependent variable and outcome. Sometimes it's a response as well. So where we can imagine there could be some relationship, like length of study is sort of represented to the exam score, and smartphone battery capacity is related to maximum standby hours. Time spent in a cab is going to be linked to the fare that you need to pay for at the end of the travel. So where this kind of relationship can be depicted in terms of some function that looks like a line or some curvature like this. So in other words, to estimate the relationship between X and Y, that is what we are doing in regression problem. And speaking of that, where there could be multiple possible shape of the line. So where you can think of a line that is parallel to the x-axis. So that is given on the first diagram. The second diagram over here, that is the first degree function. So that means where x is multiplied by a coefficient, and there is another constant as a bias that will represent the relationship between X and Y. There could be degree function for the relationship between X and Y. So it could be X to the 3, X to the 2, X to the 1, and so on. So this kind of polynomial represents the relationship between X and Y. And you can go up to as many as you want. So in this first diagram, it is depicting very complicated curvature like this. Well, anyhow, there could be multiple options that you can choose in terms of the regression model. So we were talking about some polynomial in different degree, and this slide can be understood as choosing a model. So out of multiple options, well, again, we want to start our discussion from linear regression. That means the relationship between x and y is linear. That means y can be represented as a linear combination of input components. So linear combination is a weighted sum of the input variable. And shorthand notation, it can be simply notated in this way. So using the multiplication between w and my input x, I'm going to predict my target y. So that's the idea in linear regression. In terms of a diagram, you can represent the same relationship in this way. So you have input on one hand, and they are going to aggregate it in terms of w. At the end of the day, you're going to have an output. So this fx and y is also added to the input to the function. Well, anyway, that is representing your prediction. So hat on top of y, that is representing prediction. And this simple notation is quite important because this is going to be an important building block in neural network and deep learning later on. So this kind of combination is showing up again and again throughout the semester. Well, anyhow, let's try to understand what it represents, what a linear regression represents in geometric space. So let's first consider one-dimensional input. So x is indeed one dimension, so it's actually scalar, not a vector. And in that case, well, you can imagine the first order function that we discussed in the beginning of the semester. So this is a simple line in the Cartesian space. So it's going to be a form of ax plus b, and a is the slant or slope, and b is the intercept. So using this simple line, we can represent the relationship from x to y. So given some value of x, you can predict the corresponding y value over here. And let's imagine you have a two-dimensional input vector. So in this case, you can think of a1x plus a2 x2 plus b. And this eventually draw a plane in three-dimensional space. So still, this is a flat plane in a space, and anything around this is going to be your prediction. So this is x1, this is x2, and their combination will give you a point in the plane and the corresponding value on the y-axis. That is going to be your prediction. So where we talked about model selection, so there are multiple possible degrees that you can choose, but we are going to talk about linear regression. So the degree is 1. And now we need to talk about what kind of error function that we are going to use, and also how do we perform the learning process. Well, before we get to the third part, let's briefly talk about the notation. So in the earlier slide, we have seen two different possibilities. So where f could be an input of, function of input, and at the same time, it could be a function of input and the weight vector. So where we use these two almost interchangeably. So sometimes you can omit the weight vector from the input. But anyway, both of the notation is almost representing the same thing in practice. And it's going to be the prediction y hat. And this is the aggregation of weighted sum of the input along with a bias term. So bias term is the intercept on the output space. But oftentimes, we even assume this. So one additional assumption is where there is an additional input x0 that is always 1. And by assuming this, you can write down this shorthand notation. So it is starting from 0 and going to D. And since x0 is always 1, x0 plus w0 is equal to 0. This is representing the bias term. So within this shorthand notation, you're going to represent everything. So where it is the sum of your input and your bias term. And speaking of the vector multiplication, so where x and w, both of them are a vector. So we can also represent this in terms of multiplication. So w transpose x, where the reason why we put transpose up here is where to be strict, both of them are just a vector. So it could be understood as a row vector. So w0, w1, w2, and 1, which is x0, and x1, x2. Well, multiplying this, the dimension doesn't make. So where you want to take the transpose, so w1, w2, multiply by 1, x2. Well, the notation, it should be something like this. So w, well, although I already called this as a weight, well, its name is weight or sometimes the regression coefficient. So that was a quick overview of the notation, and it's going to talk about the core parts. So the first of all, talk about the error function. So each time you want to make a prediction and you want to measure the goodness of your model. And the choice of the error function in linear regression is mean squared error. So mean squared error means where you first measure the error and take the square. And then you're going to take the average of it. So well, that's what this J function is representing. So you have average over n different instances, and you're going to compare the true y value and your predicted y value, and take this square. So that is mean squared error from linear regression model, and we are going to find out the model that is minimizing this quantity. So speaking of the minimization, that is actually the learning process where we want to minimize the W. So we want to adjust the W so that we can minimize this error. So to write down the error again, so initially we have this notation. So difference square and take the mean. Well, it can be written down in this way. So where function is equivalent to W transpose X. And where we want to optimize this J function that is equivalent to setting the derivative to 0. And if you take the derivative of this guy, where especially we want to take the partial derivative of this error term so that we can trace back the value for each W. So if you take the derivative, partial derivative of J in terms of each W, then you can come up with this. So that is easy to come up because well, you take 2 over here, so n over 2, and you take the inside, well, stay there, and you're going to take the derivative of the inner function, so that will be minus x. So eventually this is the partial derivative. Well, notice that there is an index for j, so j is representing each column. So this is the error function, and partial derivative of the error function is on the second line. So we obtain the derivative and set it to 0. And next thing we want to do is to find out W value, where again, X is given as data and Y is also given as data. So here is the unknown that we want to find out using this equation. So minus 2 over n, and take the summation over the difference multiplied by the input itself. And we want to find out some combination of W that is making this quantity as 0. So next thing we want to do is to expand it. So since these are vectors, we can expand this guy to be some hairy notation like this. This looks scary at first, but if you just follow the extension, then it can be naturally done. So initially in the previous page, we have multiple vectors, but if you extend this vector term is going to be something like this. And since this is a partial derivative, you have d plus 1 of this. So you have d plus 1 equations. And there are some routine that is there are W on each of these terms, and you have something multiplied by the input value. So you may find out there are some routine. So x0, x1, x blah 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 xj to xd, and going down 1 x1 dot 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 xj dot 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 xd. So you're going to create some combination. Pairwise combination of the input. So it's going to be W multiplied by some combinations of your input. And that is equivalent to this side. This side is multiplication of Y and X. So try to capture this form from this expansion. So earlier we talked about matrix multiplication. So matrix multiplication in a shorthand notation, A multiplied by W equals B. And solving this equation is not difficult because we can take the inverse of matrix A and bring it to the other side. So A inverse multiplied by B is going to be W. The reason I am spending slightly longer time in this expansion is to let you find out this pattern. So once you find out the pattern AW equal B, you can try to solve this problem by taking the matrix multiplication. So W is equal to A inverse multiplied by B. So bunch of different equations. And these bunch of equations can be addressed by moving one to the other and assign them and so on. So this is a system of linear equation at the end of the day. So we have seen the expanded form of this system of linear equation. And we also have seen the expanded form can be written down as X transpose X multiplied by W is equal to X transpose multiplied by Y. So solution to the above system of linear equation is simply taking A to the other side. So if you do so, W can be obtained by simple matrix multiplication. So X transpose X inverse X transpose Y. So things are quite clear, right? So this is an analytical solution, so to say. And there is a condition when this multiplication works. So this should be invertible. Well, that means the matrix X transpose X full length, that means each column of this matrix is independent of each other. Each column of X transpose X is independent. On the other hand, this X transpose X is called as a covariance matrix of X. Obviously, this condition, so X transpose X should be invertible. This is quite strong assumption. So oftentimes this is not satisfiable. So in real life, many of the columns, they are dependent each other. And many of the actual data that you play with, they are not invertible. So analytical solution does not work very well oftentimes. So we are going to see the solution for that in the next slide as well.